So just quick refresher, yesterday we talked about a vector has length and it has direction. The length is the same thing as magnitude, the direction is the same thing as the component form. If I want to find the component form, and I've got 2 points, the initial, which would be x1, y1, and the terminal x2, y2, I would do x2 minus x1, comma, y2 minus y1. So it's the change in x, comma, the change in y. It's similar to slope, but written in a different format. Then we said the magnitude, which is the length of that vector. If you have the initial and terminal, you can use the distance formula, x2 minus x1 squared plus y2 minus y1 squared. Or if I have the component form, so the result of this, we say ab. If I have the component form, I can just do the square root of a squared plus b squared. And then we talked about that we can add, and we practiced that. We added the two vectors, subtracted the two vectors, and then multiplied by a scalar, which is just the number that gets multiplied in, right? And then that's kind of, and we graphed them. But that's where we got left off. We're going to pick up there. Everything we did yesterday in component form can also be done in a form called ij. It's exactly the same, except that the change in x gets the I, and the change in y gets the j. So if I had a component form that was, let's just say it's 2, negative 3. My change in x would be 2. My change in y would be negative 3. In ij format, the 2 gets the I, and I put a comma between it. No, sorry, I put a plus sign in between it, and then negative 3j. So this would simplify to be 2i minus 3j. These are exactly the same thing. They will be used interchangeably. Sometimes you're going to get information about the vector in ij format. Sometimes you're going to get it in component form. Just know that you can go back and forth between the two. If your question gives you the question in ij format, your answer has to be in ij format. Okay, so if I gave you two vectors and I said add them, your answer should have an I and a j if the initial question had the I and the j. If the initial question was like in the brackets with the comma between them, then the answer you want to be with the vector with the comma between them, okay? So again, instead of this says horizontal component, which was the same as change in x, the b vertical component, which is the same as the y. So they are just interchangeable, and you can treat I and j just like they're regular variables. We can distribute to them, all the we can combine like terms with i's and j's, just the way we do everything else. So if I get, and this should look somewhat familiar, if I get the same kind of question that we did yesterday with a regular component form, A add u and v, B do u minus v, and C do 2u minus 3v, then sketch the resultant vector. The difference again is that this time our u is in ij format and our v is in ij format. So you actually have two choices here. One is A, u plus v. I can take u and I can convert it into component form. So 3i plus j would be 3, comma 1, because that j has a 1 in front of it, right? And v would be what? Yeah.
I is always going to be x and j is always.
Correct. So what would v be if it's 2j? What would that be in component form? 0, comma 2. And then I can work through everything the way I did yesterday. So that's your first option. The second option is literally keep them the way that they are and combine like terms, which I think is easier.
So is I worth 1?
I is just a variable, so there's no value on it yet.
So then how'd you get 3, 1?
Because this should be a J. I don't know, this font cuts it off a little bit. But there would be a 1 in front of it.
Oh.
If it's missing, it's a 0. But if it's there with no number on front, it's a 1. Yeah. So then my other option is to just say u, which is 3i plus j, plus v, which is 2j, and then combine my like terms. 3i plus 3j. So you literally can just treat them as though they're variables and combine your like terms. Now when I go to graph this, my change in x is 3, my change in y is 3. I start at 0, 0. I go 1, 2, 3 to the right, 1, 2, 3 up, Draw my vector, arrow towards the terminal point. And that's what my vector would look like. I'm going to do one where we add it just so that you can see what happens if it wasn't on, if you didn't have the actual coordinate points. Because remember, the homework has some where there's one where there's a graph and you have to actually draw it, and then there's one where you have the information and you can plot it. If I had had a coordinate grid, and I plotted U, which was 3, 1. I would have started at 0, right 3, up 1. And that vector would have looked like that. That's U. And then V, which is this 2, 0, or 0, 2. I'd start at 0. I'd go up to 0, 2. That's V. If I want to add them, I make that little parallelogram shape. So I would drag this out. Same direction as U, parallel to U, same length as U. And then I would draw this up. Same direction as V, same length as V. Where they cross is the terminal point of the sum. Now, if I had the actual measurement like we did this time, it's way easier to just plot that 3, 3 and draw my vector. But if you don't have the actual measurement, if you don't have the change in X and the change in Y, and you only have a diagram, which will happen in one of the homework questions, you've got to find it by doing that little parallelogram shape. Brian? If it's negative, it will flip direction. Yep.
How do you do like remember the few more problems?
Yep.
There's like 2U.
So when I get to 3, that's the last C on this example. That's what it is. I'll do it. Okay. All right. So then B says U minus V. So U is 3I plus J minus V is 2J. If there were 2 terms, I'd distribute the negative to both. There's only one term. So 3I plus J minus 2J is 3I minus J. Now, if I'm going to draw this on a coordinate grid, well, let me start just by drawing it by hand because we have that measurement. This would be 3, negative 1. So I'd start at 0. I'd go to the right 3. I'd go down 1. I'd connect them and point my arrow away from my initial point towards my terminal point.
The arrow is always going to be away from it.
Correct. Yep, it's always towards the end, away from 0, 0. Sorry?
Oh, wait, it's negative. It's negative, it faces down.
So now if I were to draw this, like if I didn't have the actual 3, negative 1, and I only had the same 2 starting points, so if I started, ignore this one because that was the sum of it, right? So what if I only had U and V drawn like that? Oh, I need to do that. Just ignore the line because I can't erase it the same way. This time it's U minus V. So the V changes to be negative V, which means instead of pointing it up, I point it the opposite direction. So this would be negative V. It points the opposite direction, away from the positive. Now I enclose these. This would be U minus V. And again, if you compare it to what we did on our other graph, they should be the same.
Starting point's always the origin, right?
Yep. Unless they give you different initial and terminal points. But these are, if they're in component form, starting point's always the origin. Okay, then last one. C is 2U minus 3V. So I would do 2 times U, which is 3I, plus J, minus 3 times V, which is 2J. And I just distribute like I normally would with our like terms. Distribute 6I plus 2J minus 6J. 6I minus 4J is the IJ format, which is how you want it to be. IJ format of 2u minus 3v. So if I draw that on my coordinate grid, it's a change, a positive 6 change in x. 1, 2, 3, 4 of negative y. I'm in a negative 4 change in y. And if I didn't have the first part, if it only said to do 2u minus 3v, so this is what you're asking for, Richie. And there's the question like this in the homework. I'm going to take my original graph, so I'm going to regraph it so it's cleaner. I'm going to take my originally graphed, so this would already, the picture would already have been done for you. 3, 1. This was v, 0, 2. No, that's u, sorry. This is v. So if I want 2u minus 3v, I have to double the length of u, but keep it in the same directions because it's positive. So u becomes double the length. This whole part is 2u. Then minus 3v means I'm going to flip the direction of v. So instead of pointing up, I'm going to point it down. This would be a negative v, but there's 3 of those, so I do it 3 times. This would be negative 3v. Now I close in these two. Does that make sense? We okay on the graphing? I think the graphing is the hardest because it's kind of like an abstract idea, right? It's not like a step-by-step thing.
So it's just 2u, you just double the length?
Correct. Yep. The negative flips the direction. A scalar just means stretch it out. If it was a half, I'd make it half as long. And it's not going to be, like, we have coordinate points, so we should be pretty exact. Like, I was pretty good, right? That's 6, negative 4, so that is pretty exact. But you won't have coordinate points if it's just one of the ones that's drawn, like, I forget what question it is, like number 4 or something like that in the homework. It's just drawn, and you don't know that it's going to be 6, 4. It's just drawn 2 little segments, and you've got to extend it out or change the direction and then add them together to get the ending coordinate. So if I had these points, I would go straight to just plotting the result vector. If you don't have the points is when you do what we just did. All right, so then we get to a couple of applications on these vectors. So one type of thing it's going to ask you to find is a unit vector in the same direction. So if it gives you a vector, and it's going to be in component form, and it's going to ask you to find another vector that's in the same direction, and the word unit means that it has a magnitude of 1. So it only wants it to be 1 unit long. The way we do that is we put the component form of v, so this is component form, which is going to be like this, a comma b, over the magnitude of that same vector. And remember, magnitude is the square root of a squared plus b squared. So component form of that vector over the magnitude of that vector would give you a unit vector in the same direction. So we're going to see things that say same direction but not unit. So you want to pay attention. If it says unit vector in the same direction, it means this. It means that the magnitude is only 1, and I put the component form over the magnitude. And then we'll split it, we'll rationalize it if we need to, and we'll get it in component form at the end. So that looks like this. Find again, look for the word, unit vector in the same direction as the given vector. And then verify that the result has a magnitude of 1. So we'll get to there when that's like checking it. So A gives me, U is 1, negative 3. So that is its component form. That stays in my numerator. But then I need to find the magnitude of U. It's already in component form, so I don't want to do distance formula. I couldn't if I wanted to because I don't know the initial and the terminal. So I do the square root of A, which is 1 squared, plus B, which is negative 3 squared. Square root of 1 plus 4 or 1 plus 9, which is the square root of 10. So that is the magnitude of u. And that goes in the bottom of this fraction. Now I split that up and give them both the denominator because I want it to be in component form. If that was a whole number in the bottom, I'd leave it alone, but because this is a square root, I have to rationalize. So I multiply both the top and the bottom by the square root of 10. And I get square root 10 over 10, negative 3 root 10 over 10. And this is a vector in the same direction as this, whose magnitude is just 1. So if I were to plot both of those on a coordinate grid, the slope should be the same. It should be going in the same direction. Change in x and change in y should be the same. But this one might be shorter because it has to have a magnitude of only 1. So where it says verify that it has a magnitude of only 1, it means take this and find the magnitude. So it's the square root of a squared plus b squared. That'd be the square root of square root 10 squared would be 10. 10 squared would be 100. 3 squared would be 9 times the square root of 10 squared would be 9 times 10, which is 90, over 10 squared, 100. And I end up with the square root of 100 over 100, square root of 1, which is 1. You only need to do that to check it. You don't need to do that to find your answer. Your answer is what's highlighted in the pink. You only need to do it to check your answer. So a unit vector should always have a magnitude of 1. All right, we're going to do the same thing with B. This time it's in IJ format. So my answer is going to be in IJ format. But to get it to that point, we want to put it in component form. So I want to make this negative 3, negative 4. That's my numerator. I want to put it over the magnitude of negative 3, negative 4. So the square root of negative 3 squared plus negative 4 squared, square root of 9 plus 16, square root of 25, which is 5. There's my triple dot 3, 4, 5. So both of these go over 5, and then I just split them. This time, I don't have to rationalize, but I do have to put it in IJ format. And then to verify it, I'm going to grab my component form and find the magnitude. So a squared plus b squared under the square root gives me 9 over 25 plus 16 over 25, 25 over 25, square root of 1, which is 1. All right, let V be a vector from initial point P1 being negative 2 to terminal point 2, 3. Write V in terms of I and J. So all this means is find the component form. It's just in a lot of different words. So if I were to draw this out, negative 2 is my first coordinate point. This is P1. 2, 3 is my P2. My vector would point towards P2. So this is what V would look like. To find the component form, I just have to do the second x minus the first. So 2 minus a negative 2. 3 minus negative 2. This becomes plus, and I get 4, 5. It wants it in terms of ij though, so it's 4i plus 5j. So this change in x should be 4. This change in y should be 5. If you count it out, it is. Okay, this one says, write a vector in terms of its magnitude and direction. So now this one is going to give you a vector in length. It's going to give you magnitude, and it's going to give you the angle formed with the x-axis. So the information provided to you is going to be the angle measured from the x-axis to that vector and the magnitude of that vector. The way we find the component form, so you're working backwards. This time you're going to get given a theta and you're going to get given a magnitude. Okay, those are the two pieces of information you're going to find. So if you literally had like a protractor and a ruler, I could have drawn this out on a coordinate grid. I could have said if it was 30 degrees and it's 5 units, that this would be my vector. This could be 30 degrees. The measure of that line would be 5. So if I had those tools, I could literally measure it on a coordinate grid. If it fell directly on a whole number, it would be easy to find, okay? That's not going to happen. You're not going to have a protractor, obviously, and you're not going to be able to measure it. So the formula that we use is this, and it looks so much more complicated than it is. It is just the magnitude times the cosine, God bless you, of that angle, comma, or ij, the magnitude times the sine of that angle. So this goes back to trig. Think cosine was the x, right? Sine was the y. So we're taking those angles and we're just giving them length. We're going to multiply it times the vector, the magnitude of the vector, okay? So you can either put this in ij format, where it would be like this, or you can put it in component form.
Either is fine.
It will, I think it will tell you, actually, because it's not going to be either, because one got marked wrong. So I'll check WebAssign if it doesn't tell you, okay? If it was an open-ended question on a test, both would be fine. Just realize that it'll probably tell you which one to do. So that kind of question looks like this. Find the component form of V given its magnitude and the angle it makes with the positive x-axis. So it's telling you the magnitude of V is 2 root 3 and the angle is 45 degrees. So I would do magnitude, which is 2 root 3, times the cosine of 45 degrees. I'll show you how to put it in both terms, comma, 2 root 3 times the sine of 45 degrees. Now this one, you can keep exact because that's a unit circle angle, right? What's the cosine and the sine at 45 degrees? Root 2 over 2 and root 2 over 2. So this would be 2 root 3 times root 2 over 2, comma, 2 root 3 times root 2 over 2. 2 goes into 2, cancels it out, and I get square root 3 times square root 2, which is square root 6. 2 cancels with the 2, and I get square root 3 times square root 2, which is square root 6. The only reason they're the same is because it's 45, right? So you can either write it like that, or if it was an ij format, it would be like that.
Does it matter if the I or the J comes first?
Yes, I always comes first. Good question. So because, again, like if I had a protractor and I could measure out the 45 degrees, and then I could measure out a little segment that's 2 root 3 long, and then I overlap that with something that's plotted at root 6 and root 6, those should be exactly the same angle. Then it says sketch V. To do this, we're going to just approximate. So square root 6 is not a perfect square. Square root 6 is in between root 4 and root 3. So let's say this is like a 2.3 in length. I would just approximate. Change in x to root 3, change in y to 2.3. And here's my resultant vector, which looks like it's midway between 0 and 90. That makes sense with the 45 degrees. And again, if I had measured it, it should be about 2 root 3 units long, okay? But you wouldn't be able to measure that exactly. So find the component form of the sum of u and v with direction angles theta u and theta v. And hint, find the component form separately and then add them together at the end. So I'm going to have to find the component form of u using what we just did. I'm going to find the component form of v, and then to find u plus v, I just add the two x's and I add the two y's. So to find the component form of something that has a magnitude of 5 and a degree of 0, I would say magnitude times the cosine of 0 degrees, comma, magnitude times the sine. Oh, that should be 0, not theta. 0, comma, 5 times the sine at 0. That's going to be the component form of the first one. 0 is also a unit circle angle, right? What's the coordinate point at 0? 1, 0. So what's the cosine there? 1. What's the sine there? 0. So the component form there is 5, 0, which should make sense if I literally am not moving. It's 0 degrees. I'm just going to the right 5. Now we do the component form of the other one. So it would be the magnitude, which is 5, times the cosine at 90 degrees this time, comma, the magnitude, which is 5, times the sine at 90 degrees. 90, also a unit circle angle. What's the coordinate point at 90? 0, 1. So what's the cosine there? 0. What's the sine there? 1. So the component form of this one is 0, 5. Again, should make sense because you're just going up straight on the 90 degree one. So if I want to find u plus v, this is my u, this is my v. I simply add the two x's together. So 5 plus 0, and I add the two y's together. And I'd get 5, 5. Yeah.
Are you only going to give us the angles that are on this?
No, you're going to see in a minute it changes. Yep. If I give you unit circle angles, the answers would be exact, like they are right now. If they weren't, we're going to round them. You're going to use your that's why you need calculators. So if you actually think about this in terms of, whoa, I didn't mean to do that. In terms of graphing, right? If I went and graphed the first one, 0 degrees, I went 5, 1, 2, 3, 4, 5 to the right. Up, 1, 2, 3, 4, 5 up. So this was u. This is v. And I wanted to find their sum. I would drag this line out. I would drag this line out. Where they cross is the terminal point of their sum, which if I literally overlapped it on a unit circle, on a coordinate grid, would happen at 5, 5. It should be exact. That kind of one should be exact. They won't always be exact. They're not always be as easy to find. But that one would definitely be exact. So here's some word problems, stuff like that too. We're going to get into force for a little bit, okay? This is what this is used for. These are what vectors are used for. So it says a ball is thrown with initial velocity of 70 feet per second at an angle of 40 degrees with the horizontal, see the figure. Find the vertical and the horizontal components of the velocity. So they literally give you a little picture, okay? You've got a person that throws the ball up, and it says that the angle made from the horizontal to where it finishes is 40 degrees. And it says the velocity is 70 feet per second. That doubles as magnitude. So velocity, AKA, magnitude, distance, okay? So if I want to find the vertical component and the horizontal component, how do I do that?
Use the velocity, the 70. So do you do that equation?
Yep, so this is my magnitude. My magnitude would be 70, and the theta is 40 degrees. And I just want to find them separately. So normally we put the component form in one thing, and we say change in x, comma, change in y, right? The change in x would represent our horizontal, and the change in y is going to represent our vertical. So I do 40 degrees times the cosine, nope, other way around, sorry, 70 times the cosine of 40 degrees is going to be my horizontal, because cosine is the x, which is the horizontal. And I say the vertical is going to be 70 times the sine of 40. Now you need your calculators, right? Because 40 degrees is not on my unit circle. I need to make sure my mode is in degrees, which it is. 70 cosine 40 gives me a horizontal component, 53.62. And this is in feet.
So how do you know which one is horizontal?
The x is your cosine. So think x is always cosine, y is always sine. And the vertical is 70 sine 40, which is 44.995, so that rounds to 45 feet. So there is a question like this in the homework. It literally separates it out. It says, give me the horizontal and give me the vertical. Just separate it out like we just did. Now we go a little step further. So it's going to say to find the angle and the magnitude. So we're flip-flopping this time. Now it's going to give you the magnitude, and it's going to give you the angle of it's going to give you two separate ones. If you want to find the angle and the magnitude of the sum, this is what you're going to do. You're going to find the component form of each vector separately. So there's going to be two different vectors, okay? Sometimes this is two different forces. On a dot, you'll see one where you have two different angles, okay? You're going to find the component form of each one separately, which is the magnitude times the cosine and the magnitude times the sine, we just did, okay? Then you're going to add them together, like we did before when it wanted to find u plus v, and that gives you the magnitude of the sum. What we haven't done is to find the angle of the sum. So the way you find the angle of the sum is to use inverse tangent. So I take tangent of theta equals the change in y from my new sum over the change in x from my new sum, and I inverse tangent it. So I'm going to do second tan negative 1 of the change in x, or change in y, sorry, because it's sine over cosine, over the change in x from my sum. So I gotta find the sum first, and then I gotta do this. These, I think, are the most complicated you can get, okay? And this is the application. This is where you'll see it used on force, and you'll see it used, I'll show you in a second, like it'll say something about like graph the angles. The wording on it is on the next example, you'll see. It says this: graph the vectors and the resultant of the vectors. Find the magnitude and the direction of the result. So the goal is to find the magnitude and the direction of the result of these two. So step 1 is find the component form of each of them. So I have two different things happening here. One is a 25-degree angle. with a magnitude of 400. So that component form is going to be 400 cosine 25, comma, 400 sine 25. So I get 400 cosine 25, and that's 360. Oh, let me do it in the same color. That's 362.52. Then I do 400 sine 25, and I get 169.05. So that would be the component form of the pink 25 degree angle one. Then I've got another one that's 70 degrees. So we're going from here to here. This whole thing is 70, and the magnitude of that is 300. So for that one, I do 300 cosine 70, 300 sine 70. 102.61, 281.91. That's the component form of the 300 one. So that's step one, is find the component form of each of them. Now I want to find their sum. So I want to add the two together. Add the two x's together, add the two y's together. So this would be 362.52 plus 102.61, comma, 169.05 plus 281.91. So we're adding the two vectors together. So that's the component form of u plus v. We're getting warmer. Now we need to find the magnitude of that. So I do the square root of 465.13 squared plus 450.96 squared. $647.85. So that's the first one. What's the magnitude of the result? To find the angle formed when we add these two, I do tan of theta equals the change in y this time from the sum over the change in x. So the change in y is this one, 450.96. The change in x is this one, 465.13. And I have to inverse tangent that. So tan negative 1, 450.96 divided by 465.13. And I get the angle formed would be 44.11 degrees. So this question asked for the magnitude and the direction. Magnitude is the length, direction is the angle. I'll save the force example for tomorrow. It's not in your homework. I wanted you to know it exists because you can see that later on in life. Okay, but it's not in your homework. This kind of question is, and this is where it stops. All of that 6-3 is due tomorrow. Remember, if you didn't start it yesterday, don't whine because it's going to take a long time. Okay, but that is due tomorrow at 8.
Okay.
Bye, folks.